Okay. Can you hear me? Yeah, sounds good. So, yeah, let's make a start. So let me start with a quick recap of well, where we ended yesterday. So first of all, we looked at the background evolution of the lambda CDM model, and we derived this nice formula here, which gives us the expansion rate at any redshift as a function of the energy budget. So in lambda CDM, we assume that there is a cosmological constant with an equation of state -1. There, well, is a curvature term, which in lambda CDM we typically set to 0. This is motivated by observations. We have seen this plot, which I called the concordance plot, which showed us that if we combine BAO measurements, supernova measurements, and CMB measurements, they tell us that omega k has to be very small, and for that reason, we typically set it to 0. Then there is then we split the matter content into relativistic and non-relativistic matter, and this then gives us the expansion history. So in other words, how the Hubble parameter, the expansion of space, depends on redshift. So from that, we went on and did a little bit of perturbation theory. In this lecture, I'm not going to do a deep dive into perturbation theory. I just want to give you the necessary tools to understand what we are doing later on when we modify lambda CDM, because we are going to work with fluid models, introducing additional fluids to the cosmic energy budget. And then it's important that we also perturb these fluids. So we have to learn a little bit about cosmological perturbation theory and how to perturb an ideal fluid. And that we started yesterday. So we introduced perturbations of the energy density, which we called delta rho, and we also introduced a density contrast, which is delta rho divided by the background value. We introduced pressure perturbations. We also realized that there are velocity perturbations, because for perturbed fluid, we can no longer boost into the rest frame of the fluid. I mean, at background level we can, but then there are going to be velocity perturbations, and we defined this velocity divergence, capital theta. And of course, we cannot perturb the fluid without also perturbing the geometry. So we also introduced metric perturbations, capital psi and capital phi. And this, we use the conformal Newtonian gauge, which is a typical choice in cosmological perturbation theory, although there are other gauges, and there is going to be an exercise where you kind of transform these gauges into one of each other. Okay, and then we have seen perturbing. I mean, we haven't done this calculation. It's a long calculation, and I believe you are going to talk more about these equations in the context of the CMB lecture, because there it's very relevant too. So I just stated the result, what happens if you perturb the energy momentum tensor. So you split, you see it's an equation with one open index. So you look at the nu equals 0 component, the nu equal I component, and you get two equations. I already made some assumptions about the pressure perturbations being, and energy density perturbations being adiabatic. Which means they relate to the sound speed in a particular way. We are going to motivate this further when we look at the initial conditions later. But then you get these two equations. One is the continuity equation, which tells you how the energy density changes locally. And the other equation is the Euler equation, which changes you how the velocity field changes. And you can combine these two equations into one, because you see theta, you have a theta dependence here, so you can take the time derivative of that equation, which creates a theta primed here. Then you can use that equation to substitute in the theta primed here. In the resulting equation, you are going to get a theta dependence, but then you can use this original equation to get rid of that theta dependence. So you can write down a closed form equation, well, not entirely closed form, but an equation that doesn't depend on theta anymore. And this is this equation. So it's a simple exercise, just differentiating this one, and then using that equation, you should be able to arrive at that equation. And I'm assuming that the equation of state is constant, just as a simplification for now. And what you see, this is not yet a closed form equation. I mean, it depends on delta, but also on the gravitational potentials. So we also need the Einstein equations to learn about their dynamics, and it's going to be a complicated coupled system in general. But already at this level, we can learn something. So these terms, you can think about them as gravitational source terms. And on the left-hand side, what you see, you already have the equation of a damped oscillator. And that's a crucial insight. I mean, if you have a fluid, you perturb it, this is exactly what you expect. You expect oscillations in that fluid. And this is described by this equation. And the only thing I want to do now is to look at a couple of particular cases to get an intuition of how these oscillations look like. So there's the radiation case, of course. So since the equation of state is constant, this is also going to be the sound speed. When things simplify, this damping term goes away. And what you're left with is, so this would be radiation. I give it an index R. With just this simple equation. And on the right-hand side, you're left with some gravitational sourcing terms. So again, to properly solve that equation, we need to know more, but at this stage, we can at least look at the homogeneous part of the equation if we set the right-hand side to 0. And we see that we get oscillatory solutions. So what we find is that, they are proportional to cosine the sound speed, which is 1 over square root 3 times k tau. And of course, there's also sine mode in principle, but we will see later it's only the cosine that is going to be relevant for adiabatic initial conditions. But these oscillatory solutions are really in essence the core for the acoustic oscillations we see in the CMB. So of course the full story, and you're going to learn much more in the CMB lecture about it, is more complicated, because there you do not only look at the radiation component, you have a tightly coupled fluid, as we have seen today, between baryons and radiation, so that equation gets modified, but in this kind of simplified scenario, you get an oscillator equation, so oscillatory solutions. And then we can look at matter, so another case, and there, well, this term goes away, and we are just left with that equation, delta double prime plus. So we have a friction term, and on the gravitational side we have this. And here you see this solution is not oscillatory, if you look at the homogeneous part of the equation. And so here you will learn that this leads to growing solution, so non-oscillatory. And so these are matter perturbations. And in essence, this is what then gives rise to structure formation. Again, things get more complicated because you also need to take into account the right-hand side and what it does. But this again is where this behavior comes from. And then let me look at finally at a third example, which is W minus 1. So now we are in the extreme case of a cosmological constant. So you see suddenly things start to break in that equation. We get an infinity here. So things have to be set up in a slightly different way. So instead of theta, we have to define a theta primed. So this divergence is just an artifact of how we set up perturbation theory. So it's not a fundamental problem. So if we define this theta tilde, then we see that in the case of, so we multiply the last equation, the Euler equation, by 1 plus W essentially. And then we see that this term goes away, this term goes away if W is minus 1. Sorry, this doesn't go away. And in this equation, well, we multiply everything by 1 plus W. So this becomes proportional to delta. This one goes away. But what we see is that a consistent solution of that equation is going to be that delta is 0 and theta twiddle is 0. So in the case of a cosmological constant, the gravitational sourcing drops out of the equations, and we find that no perturbations are consistent solutions. So a cosmological constant, in other words, doesn't fluctuate. It's a proper constant. Yeah. When we have? Yeah. I mean, I agree. In the case of minus 1, having the sound speed doesn't make sense as a sound speed. So then you should just look at it as a formal definition. But my point here is these perturbation equations admit a simple solution in these cases. Yeah, but that's right. I mean, I wouldn't talk about the sound speed in that case. But yeah, I promised you yesterday to tell you why we call this a sound speed, and the reason is that exactly in the radiation case, it shows up as a sound speed. Okay. So then we haven't talked yet about what gravity is doing. So this can give us somewhat of an intuition what the fluid perturbations are doing. So there are oscillatory solutions, there are growing solutions, there are trivial cases. But we also need to learn a little bit about the gravitational potential. So in principle, what you need to do is you need to perturb the Einstein equation at linear level. And this gives you a bunch of equations. And I have them in these handwritten notes all written down. But let me give you already a condensed version. So one thing you are going to find is that the zero I equation tells you that psi equals phi if there is no anisotropic stress, which I told you yesterday is kind of a simplifying assumption we typically make when discussing these things. That's one condition we are going to use. And then the other equations, again, if you make the assumption that we have adiabatic perturbations that are related in this simple way, and we assume that W is constant, we can derive a closed form equation for phi. So we get an equation which is this. So it's an instructive exercise maybe to look at the notes I put online and just derive these equations yourself to play with them a little bit and get an intuition of what's going on. And as I said, I mean, I think you're going to learn in more detail about them in the CMB lecture, but I need a few observations for our purposes. Okay, so this you get from Einstein's equations as a closed form equation for phi, if you assume that W is constant and delta P over delta rho equals the sound speed squared. And that equation we can again look at in different cases. So let's look at W equals 0. So assume we are in meta-domination. So this should be the dominant behavior. And then what you find is that okay, what happens? Sound speed and W are both 0 in that case. So this term goes away, this term goes away. And you see we only have two terms with derivatives acting on it. So we see that phi being a constant is a solution. So what we get is that we get some phi 0 plus phi 1. So you can also if you assume meta-domination, you also get this decaying mode, but that quickly becomes irrelevant because it has a negative power. So this is a constant after a relatively short time. This is one important observation about the meta era, that the gravitational potential becomes constant during the meta era. And that is true for all k. And the radiation era, here, well, we assume W is a third. And then we can solve this, this equation analytically in that case. So you can check that this is the right solution. So for some reason, I put this conventional factor of 3 here, but sine phi minus phi cosine phi divided by phi cubed, where phi is k eta root 3. And this can be expanded in two cases. So it can be expanded for small values of k, k much smaller than eta. So we just do a small argument expansion. And what we find is that we get at leading order constant behavior. So it's this phi ini. So this is why I put this factor of 3 here. So we get that. And this is true if k is much larger than 1 over eta, which is during radiation domination, just the conformal Hubble parameter. And this you might have already, something like that you might have already seen in the inflation lecture. This is what we call a super horizon mode. So this is what we mean when we say super horizon modes are frozen. So we suddenly have this constant solution. But subhorizon modes behave differently. They are not constant. So what we find there in the opposite limit, we find that we get an oscillatory solution the amplitude of which goes down like a power law. And this is a subhorizon mode. So the condition here is that k is much larger than then the conformal Hubble parameter, and this would be a sub-horizon mode. So what you see is that during radiation domination, the gravitational potential decays on sub-horizon scale. So these are two important things for cosmological perturbation theory to keep in mind. During matter domination, the gravitational potential is constant no matter what. And during radiation domination, it decays for sub-horizon modes due to the radiation pressure that acts against gravitational collapse. That's how to think about it. But it's frozen out on super horizon scales. Okay. So on super, I think I'm too high up with my writing. On super horizon scales, gravitational potential is frozen. At least what we assumed here is that W is constant. It turns out this is no longer true if W is not constant. And then you have to work a little bit harder to find a conserved quantity. And then the conserved quantity is the co-moving curvature perturbation. So it's defined as this, which is conserved in general would be this quantity, where this is the bulk velocity. And probably during the inflationary lecture, you have either encountered this one or the theta variable. So typically, people choose either of them, but they are identical on super horizon scales. So do you remember in the inflationary lecture, the conserved curvature perturbation? Did you write R or theta? Theta, yeah. Yeah, but they are the same on super horizon scales. Okay, and on sub-horizon scales, we have the statement that radiation due to its positive pressure acts against collapse. What do I mean by it? I mean that gravitational potentials decay. So whereas collapse would mean they actually grow. Okay. So this is all at this level I want to do about the perturbation theory, show you that there are oscillating solutions, there are growing solutions, and we have to make a distinction between sub-horizon and super-horizon modes. And on super-horizon scale, modes freeze out. Yeah, yeah. 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 Yeah, I mean, okay, so a few things. I mean, as I said, this is only true if W is constant. So whenever we go from one epoch to the other epoch, these quantities change, but then they are constant again. So on super horizon scales. And this is very important in cosmology because this preserves the initial conditions from inflation. This is why they are still relevant at late times, because super horizon modes remain constant. So they keep a memory of the initial perturbations. Yeah, but Yeah. Super horizon modes, we take them. Yeah. 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 Yes. They do, except for this. This one doesn't evolve. This one on super horizon scales is always conserved. So you use, so if you do this perturbation theory, use that as sort of an anchor. That's the mode that is preserved. That is ultimately determined by inflation. And the other ones are determined in relation to that. Yeah. I can show you later a little bit more details about it, how it works out, but this is the story. I just don't have time to go into too much detail about it. Okay, very good. But let's talk about initial conditions to some extent. So the second part today is going to be a little bit easier again. So the important plot here is this one. You look at, and you might have seen variations of this plot before. So this is the co-moving momentum scale, and this is co-moving time. So I always like to do everything with co-moving coordinates because then things are simple. Then the Hubble co-moving Hubble scale is just a straight line. And then the statement is that modes we can observe today, so in the CMB, but also in large-scale structure, these modes we are sensitive to with our observations, they started out being super horizon. So on that side of this dividing line. And they all must have entered the horizon at some point. So we observe them as sub-horizon modes. So this is one important observation. So in other words, when we think about initial conditions, we think about superhorizon modes. Because these are the modes we are interested in, the ones that have been superhorizon at early times. And then, so this is independent of inflation or whatever your model is of the very early universe. Inflation is just one way of providing you with these initial conditions by saying that these modes actually at some point hadn't been super horizon, they had been sub-horizon, been stretched outside the horizon. But this is a general observation. Okay, and then there's another interesting observation that data prefers a certain type of initial conditions, so-called adiabatic perturbations. And the interesting thing about adiabatic perturbations is that they are a particularly simple set of perturbations. They can be created by a local time shift. By a local universal time shift. So the time shift acts on all perturbations in the same way. I'm going to say more about it, and we can call this time shift, let's not call it eta, let's call it pi. So what we do is that eta goes to eta plus some pi, which is a function of the spatial coordinates. And if you just assume that, so if you take an homogeneous background, so you have no perturbations, and you, for some component I, and you do this time shift, so you write it as eta plus pi, what you find is that this is a small time shift. You look at small perturbations, you can Taylor expand it. So you get the background value plus rho I primed times pi of x. This is what you call your adiabatic perturbation. So you see it's small because it's multiplied by pi, and it has arisen from doing a time shift. So how to think about it? It's implementing the idea that some parts of space are ahead of time, meaning that pi is positive, and some are behind in time, meaning that pi is negative. And this is for what inflation gives you, because inflation doesn't end everywhere exactly at the same time. So it ends at different places at slightly different times, because your clock field has perturbations, and the clock field in inflation is the inflaton. And this is kind of a very simple way of thinking about it. And these types of clock fields that seed perturbations are going to be important again in this lecture at a later point. So it's an important concept. So this acts as a clock. Okay, but at this stage you can also just believe me, and these are the type of perturbations we are interested in. They turn out to give a good fit to data. And but they have a few very nice properties. So let's do it for pressure too. It's exactly the same story. You get you do the shift, you Taylor expand, and you get the derivative times pi, and this is what you call the pressure perturbation of the ith component of the fluid. And from these, you can derive relations between these perturbations. So you find that delta pi I divided by delta rho I. So then you see it's a universal time shift. So pi is the same in both cases. So if you take the ratio, it just drops out. And what we get is that this is pi I primed divided by rho I primed. And now we can just use that pi I is Wi rho I. So I use the equation of state. And what follows from this is that the density contrast of the ith component is rho I primed divided by pi primed delta j. So there's a relation between an I and j component where j is different from I, and you get this relation. So it's a certain type of universality relation between perturbations of different types. So let's look at matter and radiation. So if I is matter, then we know the equation of state is 0. So we get 1. For radiation, it's a third. So we get 4/3. So we get 3/4 times radiation. So we suddenly have a very simple relation between matter and radiation perturbations that follow from this simple idea that we have this universal time shift that creates perturbations. Okay. There's, how am I doing for time? Okay. There's also, so of course I use again the definition that delta is delta rho divided by rho bar. I use that relation, and then then this is what actually, sorry, this is rho J primed. Let me see. So actually for this one, sorry, I mean this is one condition, and this is the other condition. So it's like that. So for this equation, I just use this relation, that delta rho is this for different i's, and just take the ratio. And independently from that, we derive that. And this, by the way, is, if you remember exactly, the adiabatic condition we used when defining the sound speed. So this is why we call these adiabatic initial conditions. Okay. Very good. And there is a simple corollary we can obtain from this. So let's say we have a certain matter perturbation, and as you know, this can be expressed in terms of the density contrast, like that. And now we can make use of this relation between matter and radiation perturbations. So what we have here is that this is rho matter bar times 3/4, which is this factor times delta radiation. That's one thing we can do, and then we can start with delta rho radiation and write it as rho bar radiation delta rho. And then we can look at the ratio of these two. So how do matter and radiation perturbations compare? And so what we find is, if you take the ratio, the density contrast drops out, and we simply get 3/4 times rho m, the background values divided by rho r. So what we see is that during matter domination, when this one is much larger than this one, then also the matter perturbations dominate over the radiation perturbations. So this is quite non-trivial. I mean, so this is why I said these are very simple perturbations, because in a way, perturbations are very much aligned with the background. So if the background is dominant, then the corresponding perturbations in that fluid are going to be dominant, and vice versa. Okay. Yeah. Yeah, I mean, you are thinking about baryon photon couplings and these things. So I'm talking about now the initial conditions, right? And this holds initially. Of course, as the time evolution might do something else to the perturbations once they enter the horizon and undergo a non-trivial perturbation. So one always has to separate both things. Yeah, very good. But this is still something general to keep in mind, that yeah, you have this relation applying at least at initial times. Yeah, here, yeah, as I said, they all start outside the horizon, and then it depends on their time evolution. Then you have coupled equations. Then it depends on what particular case you look at, how these properties are preserved over time. If your equations satisfy the adiabatic condition, then this will be preserved, but they don't have to. I mean, the equations might not care about these properties of perturbations, and then things can change. So yeah. Okay, very good. But this is all I wanted to do about perturbation theory, and we are going to get back to that and borrow different ideas and concepts from that throughout the lecture. But what I want to talk about now is finally the Hubble tension. I guess that was my original assignment here. Then the important thing about the Hubble tension is that, I mean, the Hubble tension is about measuring H0. So there are two measurements and they don't agree. So to appreciate the Hubble tension and to think about physics, to resolve it, you really need to understand how that measurement is done in principle at least. And the important statement here is that measuring H0, and we have already seen that yesterday in a simple way, requires measuring distances. And that makes, of course, intuitive sense. If you are interested in the expansion rate today, you want to see how distances change as a function of time. Distances. Okay. So this brings us to the topic of measuring distances in cosmology. And an important quantity we need for that is the co-moving distance. And let me draw a simple picture, but I don't want to draw it here because then most of you cannot see it. It's kind of important. Let me put it in the box here. Okay, on the x-axis we have our co-moving distance, and on the y-axis we have eta, and we put our observer at here, and then we assume there is some source at some distance, and light travels towards us. So now I've chosen that a little bit optimistically because we know how light travels in co-moving coordinates. That's why they are so nice. Light just travels on a straight line, and that signal, light signal, is going to reach us after some conformal time. So that's eta 1, that's eta 0. And there's going to be some delta eta, eta 0 minus eta 1. And this we define as our conformal distance as a function of z, because that source is going to have a certain distance. Okay, so this gives rise to the co-moving distance. So we can just calculate it. As I said, it's this delta eta, but we can write it as an integral from eta 1 to eta 0. And then we can simply use from yesterday that a d eta equals dt. And we can write this in terms of physical time or FRW time from t1 to t0. And then we are almost there, because then we can rewrite the t integral in terms of a redshift integral, or a scale, yeah, in terms of a redshift integral. So what you do for that is essentially that you write dt as dt by dA, and then you further rewrite dA, dt by dA by dz. So you just use the chain rule, times dz, and you calculate what dt by dA is, that you can express in terms of the Hubble parameter. And dA by dz, for that you just use the redshift, definition of redshift. So what you get then is that this distance is 1 over h of z. A redshift integral that runs from 0 to z, so z being the redshift of the source, and you integrate the inverse Hubble parameter. And the inverse Hubble parameter, this was the first formula I wrote down today, we have in terms of the energy budget. So suddenly we have rewritten this conformal distance in terms of quantities which we have control over. So we have parameterized it in terms of the energy budget via the expansion history and the redshift of the source, which is also something we typically have experimental access to. Okay, but as you know, and as I've said yesterday, a co-moving distance is not helpful as a physical measure because it's co-moving, but it's not the physical distance. We need the physical or proper distance. So what is the proper distance? Well, the first thing you might say, it's just multiplying chi by the scale factor, because then you get physical distances, and that's true. So you can define a physical distance, physical as just chi of that redshift divided by a. Okay, but now you have a choice. What a? I mean, this it depends on the time when you do the measurement. So let's say we do the measurement today and we put eta 0, then a would be 1, or we have done it earlier, then it would be some time. But this already raises the problem. I mean, this is operationally not a useful distance measure, because think about a source far away, somewhere in the galaxy, deep in the Hubble flow. This would require to do the measurement of the distance instantaneously at a given time. Then I would get it. But just by using yardsticks, you cannot achieve that, because it takes you time from getting here to that galaxy. The fastest you can move with the speed of light, but even then it's not instantaneous. So while you do the measurement, the distance is going to change. So this is not a useful way of measuring distances in cosmology. So we need to do better. Okay, and this is where the generalized distances. So we are looking for distance scales that we have experimental or observational access to, not some hypothetical distance scales that are invariant but not useful. So this brings me to the distances. So let's talk first about the luminosity distance. That's one. So here, the idea is simple. The idea is that we measure some flux F, some typically of photons, but it could be gravitational waves too, of an object with known luminosity. So luminosity is the energy this source or object emits per time, L. So this is an energy per time it emits. So if we have such an object somewhere in the universe and we can observe it, and then what we measure is a flux that arrives at our position. So let's think about the static case first. So Hubble is 0. We are just in simple Euclidean geometry. we know how distances are measured, but let's do that example anyhow. Then we can relate that flux to the luminosity, and that's a simple exercise. I mean, you just say, okay, this is your source, and then it propagates radially outwards, and we are sitting here. So essentially what you need to get the flux, you divide the luminosity by the surface area of that sphere. So it's luminosity divided by 4 pi r squared. Okay, and then to measure the distance, you simply measure the flux and use this formula because you know the luminosity, and that's how you get the distance. That's how you could do it in the static case. In the static case, of course, you could just use your yardstick and measure it anyhow. Okay, but let's go to the expanding case. And in the expanding case, yeah, things are a little different because then we need to generalize that formula. Because then the flux is going to depend on the way space expands in between while the photons travel. So we have the luminosity divided by 4 pi. Well, then there's a factor of A0 squared times the coordinate distance, the co-moving coordinate distance. So I should say that the co-moving distance, let me put, because it's so important, let me put it here again for everyone who hasn't properly seen it on that side. So this is dz 1 over hz. But this, at least in the flat case, is equivalent to the coordinate distance we put in the FRW metric. It's a co-moving scale, right? So we take this co-moving scale and we multiply it by A0 to make it a physical scale. So that's the usual thing, but A0 is 1, so we can forget about that factor. And R is given by that formula. So we can calculate it as this redshift integral. So far, so good. But this is not everything. So there is now a correction coming from the fact that photons are redshifted. So they are less energetic when they arrive. So this will bring down the flux by, and redshift, we have derived the redshift formula. So the wavelengths changes in proportion to the scale factor, and scale factor is 1 inverse 1 plus z. So this gives you a factor of 1 over 1 plus z. That's the redshift. There's another effect which comes from the fact that, let's look at that one again. So let's take photon 1 that travels on that trajectory, but photon 2 is emitted a little bit later. It's emitted at delta eta later, and that travels on that trajectory. And again, because we are in conformal coordinates, they are perfectly parallel. So their time difference is going to be the same today. So that delta eta equals that delta eta. But the physical time difference between these two guys is exactly different by 1 factor of the scale factor between here and here, the ratio of the scale factors between these 2 points. In other words, because space expands, the physical time distance increases. So photon 1 will be ahead of photon 2 by a little bit more physical time, and that brings down the rate at which photons arrive by another factor of 1 plus z, again, because it's the scale factor ratio that comes in. So that is the reduced rate. And what you do now is you take this as a definition of a new distance scale. You say this defines the luminosity distance. So this is 4 pi dl squared. And dl we can now read off. dl is going to be just 1 plus z times r, where r we have seen is the co-moving distance chi, expressed like that. So you can ask, why do I make a difference between r and chi? Well, this only holds in the flat case. In the curved case, there is a non-trivial relation, spatial, or in the presence of spatial curvature, there is a non-trivial relation between r and chi. And then you need to take it into account when you go from here to here. And there's going to be an exercise where you do that. So where you generalize these distance scales in the presence of spatial curvature to understand these degeneracies in the plot I showed you yesterday. Very good. So now the philosophy is the following one. So we have a kind of theoretical expression for this luminosity distance in terms of the expansion history. But how do we proceed operationally? So dl, which is 1 plus z times this integral, is determined if we measure f, the flux, and know what the absolute luminosity is. So if we know that, we measure that, we get that, and this is how we get the distance to the object. Okay. Of course, this, when people debate about the Hubble tension and how serious a problem is, it's all about this word. I mean, how well do we know this absolute luminosity? So in the next step, yeah, we can ask how we can use that to derive Hubble. Okay. So we are close. So first of all, in the problems, you are going to derive this formula, how the luminosity distance depends on the Hubble parameter. For that, you simply take that expression and you Taylor expand it, assuming that we are at small redshift. So at small redshift, a source at sufficiently small redshift is going to satisfy that relation. So the first term is just the luminosity distance relation we have seen yesterday, but it's now generalized. So you get, sorry, you get, I'm confused. I think there's a typo in the notes. I think it's z squared times 1 minus q0, but I need to double check. Yeah, probably there's a typo. Yeah, so take that with a grain of salt, this precise factor here. But q0, you're going to derive it anyhow, so you're going to check anyhow. So q0 is the deceleration parameter, so it's positive if the universe decelerates, and it's negative if it accelerates. Evaluated today. Okay, this you can derive from this formula, and then the idea is simple. So we make a measurement of H0 and Q0, but this is not the parameter we are right now mostly interested in, but we get it as a byproduct. To make such a measurement, we fit the observed luminosity distances, which, as I said, we get by measuring the fluxes of different sources. I label them by I. And the redshifts of these sources to the functional form of DL fit to this formula. Once you do that, you find your best fit choice for the parameter of H0 and Q0. For these input values, what you get is you get H0. Okay. And the nice thing about this measurement is that it's fairly model independent, because as you will see when you derive that, you actually do not need to plug in the lambda CDM expansion history. You can just do a Taylor expansion of Hubble, which works if Z is sufficiently small. So for low redshift sources, this becomes a fairly model independent statement. And you also see here, this is just the coefficient you get at higher order in the Taylor expansion, because you get if you expand it, you get H dot terms, which depend on A double dot. This is where the Q0 is going to come from. But you're going to see it when you make the calculation. So I'm no expert on the measurement side, but let me state a couple of the important results in that context. So what do people use as these known objects with known luminosity? So by the way, these are called, and that's an important notion, these are called standard candles. So typically what is used are Cepheids, which is a type of very bright star that have a certain period brightness relation, which allows you to normalize them. Or even brighter type 1a supernovae. And if you use them, what you get is this infamous value of H0 in units of kilometers per second per megaparsec of, if you believe the Shoes team, you get 73.04 plus minus 1.04. And if you trust the CCHP team, they have a different way of calibrating this L, of knowing it. They instead, the Shoes team uses Cepheids as standard candles to calibrate it. It's called the distance ladder. So I won't have time in this lecture to go on in the details of the distance ladder. That would be a lecture on its own. But there is one page in my notes devoted to kind of explaining the philosophy of the distance ladder. But they get a lower value, 69.96, but with significantly larger error bars. And that's their latest value they put out in a paper a couple of weeks ago. And this value is really what people mean when they talk about the Hubble tension. And this value is the value which gives rise to a lot of debate, because this, you see, is much lower. It has larger error bars. It's compatible with that value statistically, but it's also compatible with the lower value we get from CMB, as we will see. But just to give you an idea where the debate comes from. But the interesting thing is that there's progress on this side, because this team is using new data from the James Webb Space Telescope, and they still have very relatively small data sets to get to this value, and they are accumulating more data. And yeah, so this should improve over time. I'm hopeful that in maybe a couple of years we know more. But I have said that already 5 years ago, so that again has to be taken with a grain of salt. So that situation is is now going on for, well, almost 10 years, that there are these two measurements that don't quite agree. Okay, that's one measurement, or one distance scale. There's another one, which is the angular diameter distance. Here the idea is to measure angular size. That's the idea. Of known physical scale, which I call capital D. And this is also what we call a standard ruler. So instead of a standard candle, where you know the brightness, you use something where you know the physical scale. So the picture is that. So take a plane. Time moves upwards, so that's a spatial plane. And then we have some source sitting somewhere in this plane, and it has a certain, corresponds to a certain length scale, d. And we are sitting here, we are the observers at a later time. And what we observe is this, this triangle. I mean, what we observe is the angle under which we see this distance scale down here. That's the idea. Okay, how to derive it? Again, we look at the static case. Then it's easy. In the static case, this angle is just, well, if it's a small angle, but typically we have to deal with objects that appear under an extremely tiny angle, is just d divided by the distance. And how do we generalize it? Well, in this case, it's fairly simple. We just generalize it by saying it's the physical scale divided by the co-moving scale times the scale factor. And this then defines the angular diameter distance. So in analogy to what we did before. And then the idea is that a measurement of h naught, there the idea is fit d by dA, which is 1 plus z over chi of z, so just using this formula, times d, to the observed angles, which we have at different redshifts. And by doing that, again, we get the angular diameter distance. And then by knowing how it is defined, we learn about the expansion history. So because dA here is just 8 times. Okay. So the question, of course, is what is that standard ruler? And the answer is going to be, it is related to these oscillations I've been talking about in the first part today. It has to do with the sound horizon related to these oscillations. So that's the story I'm going to tell. This. So let's talk about the sound horizon. And again, you will learn more about the sound horizon in the CMB lecture, but we still need it. And for that, we consider toy model. You will do a more realistic model in the exercises. I mean, yeah, I let you do all the hard work, actually. I'm so sorry about that, but otherwise I'm never going to finish what I want to say. So consider toy model for acoustic oscillations. So if you just recall the equation I wrote down before for radiation, it was this. So this is just if you have a radiation fluid and it feels the impact of gravity, and you set the sound speed to the adiabatic sound speed, so it's a third. Then, and let's assume we are during matter domination, so we are already close to where these photons decouple, close to recombination, say. So this is small, and then we have learned that in this case, the gravitational constant, the gravitational potential is constant. That you remember I showed you when we looked at the closed form equation for the gravitational potential, that during matter domination, it admits this constant solution. And then we can solve this equation. And what we find is that it's just, I mean, a standing wave solution. And I think Rishi also mentioned that. K eta plus sine, so another coefficient, B sine K eta minus 4 phi, which is the constant. So if you plug that in, you immediately see that this is satisfied. This term goes away anyhow because phi is constant, and then this takes care of this term. I'm canceling the contribution from here. So this is what you get. But now one important thing is that adiabatic initial conditions, I'm not going to derive that, but this is one of the important results in cosmology, and you will most certainly, I mean, it was mentioned in the CMB lecture already today that the photon perturbations are only cosine perturbations. So this one goes, so B is 0 for adiabatic perturbations. And this is exactly what you find if you take these initial conditions I showed you before, and you use them to fix this solution at superhorizon scales. But of course, that requires more work. But then what you find is that B is 0, and A is given by the initial value. And if you do it carefully, you find that A is 4/5 times the initial curvature perturbation. And I think what you did in the inflationary lecture, you looked at the theta variable, and you calculated exactly that. I mean, a statistical statement about this quantity. And this is how you see how concretely the inflationary physics fixes the initial conditions or the perturbations in the primordial fluid. I mean, in this kind of simple toy model, why do I call it toy model? Because I'm not taking into account baryons here. So in the exercise, you're going to look at the coupled fluid, and that is going to give you a more realistic estimate of the sound horizon. but we get a good enough estimate right now. So yeah, what is the sound horizon? Well, the sound horizon is the distance these waves can have traveled by the time of recombination. So it's, or decoupling, better to say. So the sound horizon is 1/√3, which is the sound speed, times eta decoupling. That would be in the simple model, the sound horizon. And yeah, and the picture, and you have already seen it this morning, is the following. So if we look at a function of time, we have these oscillations. So if we look at the function of log A, so at early times, the cosine goes to 1. So if this is in units of the initial value, then these perturbations look like this. And let's say decoupling is here. So you have different perturbations that behave differently. So let me take a different color for a different mode. And that mode might be such that it just hits the minimum at that time. So what you see that at the time of decoupling, you are in a different point of the phase of these oscillations for different K modes. So in that case, yeah, we have some K and we have some K primed. And this is the snapshot we take when we measure the CMB. So here the photons decouple, and well, we get they can decouple in a high density region or in a lower density region, depending on what K mode we look at and where in its, I mean, what the phase difference was in its cosine oscillation. Okay, but this is just the overall physical picture that gives you the sound horizon, and so the peaks in the CMB will correspond to the points where the cosine is either -1 or 1. So it's n pi divided by RS. So this is why the sound horizon is such an important quantity in cosmology, because it relates to the peaks in the CMB, and you can imagine measuring the amplitude and shape of the CMB is complicated, but measuring the peaks, it's a very clean thing to do. So this is why we have such good observational handle on the sound horizon. Okay, and I should say this was a toy model, so more realistic is that the sound speed is not just a third. And this is exactly due to the fact that you couple baryons to photons. The baryons are almost perfectly pressureless, so you can approximate them with an equation of state of 0. And this means, and that you are going to derive in the exercise, that you have a sound speed that becomes time dependent because you have a 2-component fluid. So also relating back to the exercise you did yesterday. And looking at it as a 2-component fluid, you can generalize the definition. So then the sound horizon is the integral d eta of the sound horizon. Of the sound speed from 0 to eta decoupling. And that you can write as the set integral from decoupling to infinity of the sound speed divided by Hubble. So this is again using this usual, what we have done already several times, dividing an eta integral into a redshift integral. And this is really the very important formula to keep in mind. This is what we this is the object we actually constrain and measuring the CMB. So there you have, the sound speed is close to that, what I got in the Tor model, because the photons, as we have seen today, they are fairly dominating this coupled fluid, but it's not perfectly like that. So there is some set dependence. And if you take this into account, then you are going to find, if you assume the lambda CDM model, you get a concrete number for this. So for lambda CDM, you get 147 megaparsec. So the sound horizon, by the way, the sound horizon, this is a co-moving scale. To get the physical scale, we still have to multiply it by the scale factor. But this is then what you get if you assume the lambda CDM model. And in the exercise, you are supposed to reproduce that value. It's quite instructive to see that you get a very concrete number by not making too complicated assumptions of the model. So what you're going to do, you're going to look at the generalized perturbation equation and then derive the sound speed and simply plug it in here and then calculate it. Okay, so this is the sound horizon. And the sound horizon, by the way, we do not only measure it in the CMB, we also measure it at later times in the matter power spectrum. It imprints itself in both the matter power spectrum and the CMB. But let's talk about the CMB first. So how am I doing for time? Not good. Okay. So in the case of the CMB, we measure the peaks. So we measure what we get from the CMB is the angular size corresponding to the peak positions, which is, as I said, RS divided by Z decoupling. And that is the most precise thing we get from the CMB. So it has an error of less than 0.04%. I mean, this is as precise as it gets in cosmology. That is quite fascinating. Okay, and now how do we get Hubble from this? Well, so we know what the sound horizon is. It's 147. We know this guy with high precision, so let's find out what this one is. And here it's at decoupling, so it's 1100, so we cannot assume lambda CDM. We have to assume lambda CDM. We cannot assume that it's model independent. We just do a Taylor expansion. So what we get is that well, we can rewrite this integral, which you have now seen several times for this co-moving distance. We can write it in the following way. Square root, let me just finish that then. H squared minus Wn. I'm going to explain what these things are. Okay, so I introduced this little h. Little h is defined as the dimensionless Hubble parameter. So it's defined as capital H is little h times 100 kilometers per second per megaparsec. So this factor is just a number. It doesn't have a dependence on the Hubble parameter. It's just a convenient way of working out the dependence on Hubble. And what's the little omega? The little omega is our capital omega times little h squared. So that is important because then you remember capital omega depended on h naught as 1 over h naught squared. So multiplying it by little h squared means this little omega is independent of Hubble. So it's an independent measure of the matter energy density, which is independent of Hubble. So if you want to know how Hubble is constrained by measurement, we should express everything in terms of quantities that are independent of Hubble. So what we see, this is what you get for this omega lambda factor, if you use that omega lambda is 1 minus omega matter. But what you get is this simple formula. And now you see why, how we constrain the Hubble parameter with the CMB measurement. Because this quantity depends on Hubble. So yeah, just a second. I know what this is. So now I only need to know what omega matter is. We know the redshift. I mean, we can just perform that integral. And omega matter, that you will learn in the CMB lecture, little omega matter is, well, is constrained by relative heights, absolute and relative heights, I should say, of CMB peaks. So the CMB is of course a very complex observable with a lot of data points, and you are fitting this kind of simple, I mean, you're doing overall a way more complex fit, and that gives you omega m independently. But this shows once you have that, then this completely fixes little h. There is no further dependence. And then you, unless you have spatial curvature, so this is without spatial curvature. Once you have spatial curvature, you again have this geometric degeneracy. And then what CMB gives you is this value, 67.36 plus minus 0.54 kilometers per second per megaparsec. And now if you do the math and look at the difference between this measurement and the shoes measurement over there, and you divide it by the square of the arrows, so 0.54 squared plus 1.04 squared, what you get is a 5 sigma tension. And that is what people call the Hubble tension. Okay, that's a good place to stop, I guess. Thank you. Questions? Mm-hmm. Mm-hmm. Absolutely. So we have to start from there and reach here. If we want to introduce new physics, yeah, then we have to start from there and go here. If we, sorry? Get those values. Yeah, exactly. So that's very important. So this whole CMB story is lambda CDM dependent. This has very little model dependence. So if we trust these values, then the obvious way to go is to modify the lambda CDM model in such a way to increase the CMB prediction to one of these higher values. And these are exactly the two directions people are working on. Some people like me are interested in playing this game of modifying lambda CDM. But another equally important, or maybe even more important approach is to question these values and understand what's happening there, but maybe also look at the CMB value, understand systematics. And as I said, I mean, known luminosity is exactly the caveat here. I mean, it's a highly non-trivial thing to know the luminosity of type 1a supernovae, because you have to calibrate them first. So, and in order to calibrate them, you need the distance layer. So in principle, how it works is that you start by Cepheids, which are not as far away as these type 1a supernovae. So you first calibrate Cepheids using parallax. Then you know them as standard candles. Then you look for host galaxies of Cepheids together with type 1 supernovae. So you use the Cepheids to infer the distance to these host galaxies. and then you use that knowledge to calibrate the type 1a supernova. That's the second rung of the distance ladder. And then you use that knowledge to go to supernova even further away, deep in the Hubble flow, to infer, to play this game of calculating H0. So this is, there has a lot of the work has been done on that, on the distance ladder. This really would be a lecture in itself, because there are different choices of how you calibrate the distance ladder. So I mentioned now Cepheids, but other groups, for example, use a different type of stars, tip of the red shine branch stars. And yeah, there are astrophysical uncertainties you need to understand. It's a complicated business. But I'm hopeful that we are going to see kind of improvement and convergence there in the future. And I should say, there's another type of standard candle which doesn't rely on electromagnetic signal. You can have neutron star mergers that emit a gravitational wave signal with an electromagnetic counterpart, and then the same reasoning applies too. I mean, if you know the masses of the mergers, you know the luminosity, you measure the flux, and you infer the distance that way. And this is where the community places its hope on ultimately, that they are called standard sirens, that they are going to fix this. Yeah, I went a little bit quickly here. So, so what we have seen is that chi of z is just the z integral of 1 over h of z, right? So h of z you can write as square root of, that was the first formula we had today. So there's a factor of h0, and then it's omega lambda plus 1 plus z cubed omega matter. So I can drop omega radiation, because by the time of decoupling, omega radiation is already fairly highly subdominant, but I can also include it. It doesn't matter. The integral picks up its main value at relatively late times, so we can ignore radiation. And then this just follows by using these two definitions. So I take h0 back under the square root, then it multiplies, h0 squared multiplies omega lambda, and that gives me the little omegas. And I'm also using that omega lambda is 1 minus omega m. This is what we have seen yesterday. And then you get this formula. Yeah. Yeah. Yeah.
This will be insensitive to the equation of dark energy, the equation of state of dark energy.
Yeah. Completely independent of that. That's another important thing. We are going to talk about it more tomorrow. Where is it? The sound horizon here. It's a redshift integral from z decoupling to infinity. So it's absolutely ignorant about what happens in the late universe. It only depends on early universe physics. Yeah, okay, I was a little quick here, but so this is also something I think you are going to learn in more detail, but if you look at the CMB, you do this, you look at correlations in the temperature anisotropies, and you do a Fourier transformation essentially on a sphere. So these are your spherical Fourier modes, these L, and you get this power spectrum. And it comes with these peaks, and each of these peaks corresponds to one of these values of the co-moving momentum, right? But you can then L, since it's a Fourier transformation on a sphere, there's a dictionary between L and an angle. And you use that. So you read off where is that peak, you convert it into an angle, and that gives you theta. That's what you conceptually at least do. For the first one, yeah. But I mean, of course, you see the other ones are trivially related to the first one, and the difference depends on the sound horizon. So you can use any of them to infer the sound horizon scale. You just need to take into account which is it the first, second, or third, and so on. Yeah. But the physical pictures, you have these oscillations in the primordial fluid. At the time of decoupling, they can be maximally dense or maximally diluted, and both cases correspond to peaks in the spectrum. Yeah. And the sound horizon really is the characteristic scale that determines which K mode has a peak, and I mean the K dependence. Yeah. Yeah. I mean that it all plays together. Yeah. I mean, of course, you also have the sound horizon here, but the argument kind of changes, and this formula changes because you have a phase suddenly. So you can describe this additional term as a phase you add here in the cosine, and that there are constraints on such a phase, so it has to be fairly small, absolutely. And yeah, that's right. Very good. I didn't have time to talk about it, so I'm glad you asked. Yeah, BAO is a very similar story. So here, the sound horizon scale gets imprinted into the CMB photons, but these acoustic oscillations, I mean, it's a coupled fluid, right, between baryons and photons. So although the baryons undergo these oscillations, and they imprint it in the matter power spectrum. So there are subtleties, and I think Rishi towards the end was exactly pointing out these subtleties. I mean, the sound horizon scale is not exactly the same as here. So here we integrate to decoupling with the baryon sound horizon. You integrate a little bit further. This has to do with this fact that for the baryons, you look at velocities, so it's the sign, and then you have this pile-up effect. But then then the rest conceptually is exactly the same. You calculate the sound horizon for the baryons. It's called sound horizon at radiation track. You calculate that, and then what we observe again in the BAO measurement is an angular scale. But what is important? Maybe I should say that BAO measurement is a much smaller set, and that's of course exciting because it makes that part, I mean, the sound horizon is still dependent on early universe physics, but the co-moving distance is less dependent. So in BAO, you again constrain BAO, you constrain the angle, which is the sound horizon at what is called radiation track divided by the co-moving distance, but this time at BAO and not recombination. So this is more a number of order 1. And then you can Taylor expand this again, at least if you look at BAO measurements at fairly small redshift, smaller than 1. And what you get is approximately that this becomes just 1 over h naught. So what you constrain is actually that you get a relatively direct constraint on h naught times rs. And I think, Purba, you are an expert on inferring constraints on that quantity in an entirely model agnostic way from BAO and supernova, uncalibrated supernova data, right? So there you get constraints on that. And if I understand you correctly, they are now at the order of a 1% error, right? So you get that this has to be some constant with an error smaller equal 1 to 2% probably, so, something like that. So it's also a fairly well-constrained quantity, and it does it in a different way to CMB, and that's going to be important. Yeah, thank you for asking that, yes. Mm.
Increase the value of Hubble constant, then what we should do is increase the value of R.
That's absolutely right, yes.
So from the BO measurements, do we have any bound on RS that how much it can be?
Yeah, that's what I mean here. I mean, the BAO doesn't constrain RS directly or H naught directly, it constrains the product. And we know it does it at this 1% level. So this is what we know. And so if we know how much we want to raise Hubble, we want to raise it by 5 to 10% to resolve the tension. Well, we find we need to lower the sound horizon by 5 to 10%. And yeah, in order to not run into trouble with BAO. Yeah. That's the story there. Yeah. I mean, it doesn't mean other things can happen too. I mean, I think it's more like a necessary condition. It's not a yeah. You can also change the expansion history at late times and so on, but it's hard to see how you can avoid that. Yeah.
So at late time, you want to increase the value of Hubble constant or early time? Which one is more preferable?
Okay, can you ask again?
I'm saying that
Yeah.
the way to resolve Hubble tension is
Yeah.
either decreasing the Hubble constant measure at late times,
Yeah.
or increase the Hubble constant measure at early. So which one is more preferred?
Yeah, I mean, these are very, yeah, it's hard, it depends on the part of the community. If you ask cosmologists like me who's interested in doing model building in the early universe, I'm of course more inclined to go down that path, whereas someone who is more astrophysically inclined is going to think about that. And both, I mean, I'm not saying we should do the one or the other. Both things are equally important. And maybe also thinking about possibilities to kind of circumvent these arguments in a clever way is also interesting. So yeah, that very much depends on what you're more inclined to doing. But if you want to learn about new physics, and that's the exciting opportunity here, then I think this is at least the obvious way to go. Yeah. And this tension is around now for 10 years, I would say. So I think it slowly is getting time that we think about what it might imply for the physics of the early universe. At least that's as I think, a very exciting opportunity, especially given that there are so many things we still don't understand about lambda CDM. So it might be a clue, a signature. The Hubble tension might be a signature of new physics. Doesn't have to be at the end of the day, but this is the possibility I'm interested in. Yeah. Yeah. I mean, okay, early has a very clear definition, before decoupling, because the sound horizon only depends on physics before decoupling, and late is everything after decoupling. Okay, now if you look at concrete models, things become trickier, because when you introduce new physics, it might have an impact at early times, but also at late times, and then the interplay between both things plays into this Hubble tension game. So of course, by doing late time modifications, so by late time I just mean after decoupling, you are also going to change the prediction for H0, and you can move it both ways, but there are limits to how much you can move it by only looking at late times. So the final answer might be a particular model which does both. But of course, to learn about how to think about the problem and come up with new physics, it's important to kind of, in a clean way, figure out what the mechanisms are. And this is really the idea of this lecture. I mean, where are the obvious dials we can play with to make progress with this problem? And yeah, and I think the obvious dial is going to be the sound horizon. So in this lecture, I'm going to focus on models that that reduce the sound horizon. And in order to respect that bound, they are going to imply a larger value of H0. But it's not as, yeah, we are going to see yeah, this is not a trivial thing to achieve. So yeah, I mean, but this is really what people are working on nowadays, and this is one direction. So I don't want to give the impression this is the only thing you should be thinking about, but I think it's a fruitful direction, and if the Hubble tension remains. Yeah. Okay, thanks.